Today, presenting joint work with Dylan, and it's about instance-optimality in interactive decision making. Andrew, stage is yours.
Yeah, thank you for the
Full screen.
Well, we'll try to do that. Thanks for the invite. Yeah, excited to be here. So as Thomas said, this is joint work with Dylan Foster, who's at MSR. Okay, cool. So we're going to be looking at basically instance-dependent decision making, and so I kind of want to start out with some motivation for why we would want to think about instance-dependent decision making. So say we have some problem, and our goal, we want to train an agent to navigate in some unknown environment. And to make this concrete, let's just say, we want to train it to drive around some road. And our goal here as sort of algorithm designers is to basically come up with an algorithm that sort of allows this agent to learn to navigate an environment as quickly as possible. But there's, I think, one caveat which sometimes we don't think too much about. Is when we're actually deploying this, we want it to navigate as quickly as possible, like on the specific environment of interest. So while we do want sort of general purpose algorithms, which are broadly good across a class of environments, when we deploy it, we're deploying it on a specific environment, and we want it to do well on that specific environment. Now, I think as algorithm designers, often what we think about is designing algorithms that sort of learn to navigate as quickly as possible on the worst case environment in a class. This would be like sort of a minimax style result, right? We want to say, okay, give me a class of instances. I can come up with an algorithm that on the hardest instance in that class will do well. And then the thought is if it does well in the hardest instance, they'll do well in the easy instances too. However, this is not actually always the case. I mean, it will do well in the easy instances in some sense, but it isn't the case that if you can perform optimally on the hard instances, you'll perform sort of optimally on the easy instances. There may be sort of instances that are significantly easier, that if you have an algorithm that is optimal for the hard instance, it's not going to exploit the structure present in the easy instance. And we can actually show this provably. Like it's not hard to construct examples where something like this will be the case. And so what we care about, what we really want to think about then is sort of developing algorithms whose complexity scales with the difficulty of each given instance, right? So in particular, like with these road examples, a circular road presumably is much easier to learn on than this much more complicated road with all these terms. And so we would like an algorithm that the complexity of learning on this simple road is significantly less than the complexity of learning on the more complicated road. And also that that it scales reasonably to the more complicated road as well, but that it's really sort of taking into account this instance-dependent nature and how it's learning. And furthermore, and sort of what we're talking about in this talk a little bit, we really want to show that the complexity is optimal on a particular instance. So we want to show that on a given instance, we can sort of do as well as any like reasonable algorithm would on such an instance. Okay, so we're going to be looking in sort of the setting of interactive decision making. And interactive decision making is in some sense a generalization or an abstraction of RL. So we have some agent and we have some environment. And at every step t, the agent will choose some decision, pi t, from some set of decisions, big pi. And the environment, the environment will then sample a reward, RT, in an observation, OT, based on the decision that was played, pi t. The agent will observe the reward or observation, and they'll choose a new decision. And this will proceed through t steps, big t steps. And what we'll do is we'll sort of look at, okay, so we'll have a particular instance, which we'll denote by M star, and we'll have a model class M. So going back to sort of this car example, the model class would be the set of all these cars, all these tracks I showed. The particular instance M star would be, say, the circular track. And so we'll encode our prior knowledge of the problem in this model class. And then what we're interested in actually learning on is in some particular instance M star, which we assume is in the model class. So we'll just define a few pieces of notation. So Fm of pi is sort of the expected reward, plain decision pi on model M. Pi m is the optimal decision on model M, basically the decision that maximizes reward. Delta m pi is the gap for policy or decision pi on model M, and delta min m is sort of the min gap on model M. And what we're going to be interested in this talk is minimizing regret, and we define regret sort of in the standard. So just to like make some connections, for those of you familiar with some of the work Dylan's been doing over the last couple of years with this DEC stuff, this is a study from this DEC paper. And it's really an abstraction of RL in some sense. So we can show that sort of all the standard decision-making problems we like to think about fit in this. So just as a couple examples to make this concrete, you can multi-year bandits sort of fits to this in a very straightforward way. M in this class is just the multi-year bandit. Pi would just be the set of actions. So we have A actions, just A elements of pi. In this case, the set of observations is the empty set. We don't have any real observations. And the rewards just say some values in 0, 1. But this also encompasses RL. So in this case, M, the model is an MVP. Pi would be a set of policies now. So it's not a set of just actions, it's a set of policies. Now the observations is the space of sort of all possible trajectories. So how this would work for RL is you play a policy. This policy interacts with the environment, and then what you get out is an observation that is the trajectory, the sequence of states and actions you visited. And then the reward is simply the entire episode, the entire reward of the episode. So that's really what we care about at the end, is sort of maximizing episode reward. So that's R, but O is sort of all the at every step what is going to be. And this setting is quite general. And so it encompasses many other problems, linear bandits, structure bandits, RL with functional approximation, etc. And the idea behind like looking at this setting is it's kind of like abstracts away some of the like intricate details of looking at each of these settings individually, and allows us to come up with a more general understanding how to do decision making. And so our goal then in this talk is really trying to understand, sort of get a general as well as finite time understanding of instance-optimality in this interactive decision making setting. And I guess I want to emphasize both of these parts again, the general and finite time. So we really want to develop sort of general algorithmic principles that apply to any class of script M. So if you have a problem, you can encode it in script M. Maybe this is a bandit problem. Maybe your problem is a bandit problem. Maybe it's an RL problem with some particular structure. Whatever. You encode that in script M. What we want is we want to come up with an understanding of sort of the complexity then associated with instance optimality in class script M, and then come up with algorithmic principles that will apply to script M regardless of what this is. And we want to do this in finite time. So existing work tends to either specialize to particular settings, multi-year bandits, linear bandits, capital RL, etc., or is extremely asymptotic. And so we kind of want to knock out both these things, thinking about instance optimality in very general settings, as well as sort of what the finite time properties of instance optimality. And sort of our contribution, which I'll get into for the rest of the talk, we come up with sort of a novel complexity measure, which we call the AUC, the allocation estimation coefficient. And we can show that in some sense this really characterizes the finite time complexity of instance optimality in these very general decision making settings. Okay, before I dive in, any questions like on the setting, the goals? Yeah. Can be finite, can be infinite. Yeah, like the results we prove. I won't go into some of all the technical details of this, but like the results scale with like the log covering number of M. So if it's some like non-parametric class that is like massive covering number, then like the results will degrade significantly. But like in general, it could be infinite.
Is this class also containing the model free?
It's a good question. So in some sense, yes, like the DEC paper does stuff with model free. What we're going to actually look at, though, it's not clear that this extends to model free. So the sort of when you start thinking about instance optimality, the way people usually think about it is really a very model-based notion. So I think this is a very interesting direction for future work. Yeah. Anything else? Okay, cool. Okay, so it turns out that there's actually kind of already an understanding of instance dependence, instance optimality. And this actually is very classical. So this goes back to 1997, work of Graves and Lai, same Lai as Lai and Robbins. And they proved in this paper from 1997 that there's some measure of complexity, which depends on the model class and the model. So I denoted this by GLC, Graves and Lai complexity, script M and M star. Such that any like sort of consistent algorithm, if you can just think of a sort of a reasonable algorithm, must have regret that scales at least as this measure GLC times log T. And again, this is this is capturing the properties of the particular instance. So it's saying on this particular instance M star, you need to pay this regret. And there's been a lot of work then since this result, and especially over the last decade, in showing that this is tight. So we have a lot of algorithms out there. I cited one recent paper on this. This is from 2022, but there's a lot of other papers that shows that this is tight, that you can sort of upper bound the regret. You can come up with an algorithm, such that the regret for this algorithm on M star is upper bounded by this constant GLC times log T. And so in some sense, you can look at this and be like, well, this is actually, I mean, we're kind of done, right? Like this is what it is. Like this GLC quantifies instance optimality. And that's not quite the case. And so I'll get into that in a second. But first, let me just explain a little bit of what this constant is saying. So, okay, here's the mathematical definition of it. It's not actually too important that we fully understand the mathematical definition, but the intuition behind it is the following. There's basically, it's an optimization problem. And you're optimizing over allocation of data. And what this is an allocation on the poles, or sort of the number of poles you're allocating to decision. And what you're doing is you're trying to minimize regret such that you can sort of eliminate instances with different optimal decisions. So in words, all this says is that the GLC constant is the minimum regret needed to distinguish M star from every model in my model class that has a different optimal decision in it. And this is, I think, pretty intuitive because, like, if you want to do the right thing on M star, you need to show that that's not optimal is not optimal, which is kind of equivalent to just eliminating these instances with different optimal decisions.
So we are showing that the action space is finite here.
Yes, that is. We are assuming action space is finite. Yeah. Yes.
Yeah, sorry, I really want to know what consistent means.
So it means that you have sublinear regret on any instance in the class. So, and what this is doing is just sort of eliminating like pathological algorithms that are just like playing the optimal action on M star. So we need to sort of get rid of that. And so you say, well, on any instance, it will at least have like small o of T regret. Yeah.
And GLC is the minimum regret needed to distinguish M star. Why is the minimum, to me, the top set, the minimum regret is log bounded by GLC times log T. Why would it not just be log bounded by GLC?
This has to do with like, okay, you can think about, say we had a finite, and or say we want to do something in high probability, then this log T would be a log 1 over delta.
Sure,
so we're doing.
We've already distinguished M star from all M and GLC.
Right.
So we're done.
So the thing is, if you look at the mathematical definition, if we wanted to get a high probability guarantee on this,
No, I just want to regret.
right. So, but like, we want an expected regret guarantee. So we can think about getting like a high probability.
So expected regret is regret, right?
Yeah.
Yeah.
Okay, so like, I mean, maybe one thing to just like abstract away from the technical details, like, for instance, for multi-arm bandits, you always have these bounds that are like log T regret, right?
Sure.
Same thing going on here.
By definition here, by the time you suffer GLC regret, you can now distinguish M star from everything else.
With constant probability. So GLC sort of quantifies in constant probability, but as T gets large, you need to sort of do this with probability 1 over T. That's why you get a log T. Yeah. Do you have another question, Chava?
I had actually. Maybe.
Okay. Okay. Anyways.
Oh,
Yeah.
it does kind of follow up to Dave's
Yeah.
question, which was about this consistency definition. You could change the consistency definition. You could tighten up. Would it change the result?
No, I mean like the precise definition of the consistency kind of comes into this term. Like this term will change a little bit depending on how you maybe define this. I mean, again, if you just allow for pathological algorithms, then yes, it would, because like you can't get any lower down there.
If you remove, let's say, algorithms which are overly bad, so they are barely sub-linear, like, and you just like keep the algorithms which are nearly the max. I would think that this changes a little bit.
I don't think so. I think like the fundamental thing is still, I mean, how you prove this lower bound is like you just say that like, okay, if I have algorithms that are doing, that are getting sublinear regret on instance A and instance B, and instance A and B have different optimal decisions, then in some sense, this algorithm has to distinguish between instance A and B. And so like any sort of class of algorithms that is doing something reasonable would have that property. That's all you need.
I'm thinking is that if you have a smaller class of algorithms, shouldn't you be getting?
So if you had like, if you say that you're restricting your algorithms to square root Q regret, then like you would still have the same property. This, what I'm finding in a little o would be better. That's where that's going to come in. So it would change, but like the leading order term isn't going to change.
Because it's all asymptotic.
Yeah, this is what we're going to get into, but yeah.
Okay.
Yeah.
Sorry. I guess I was thinking on a non-asymptotic version of this. That I think you will see.
Yes. Yeah.
Okay.
So in some sense, so we're just kind of taking this as given. Like this is kind of known. The lower bound, we didn't prove a new lower bound. I mean, well, not for the leading order term. Like we're just kind of taking this lower bound as a given and kind of working in this framework in some sense. But there's definitely questions even there with like, yeah. But I think, yeah, you'll see as the talk goes on. Okay. So just as an example of what this constant scales as for multi-arm bandits, it's the sort of familiar sum 1 over gap scaling that we've all probably seen. And then this then generalizes to much more complicated settings. You can't generally write this down in closed form though. Okay, so yeah, so the question is sort of the Graves and Lie complexity of the whole story. Like that result I just showed sort of gave you like a tight characterization that says as T gets large, the Graves and Lie kind of is a lower bound and an upper bound. So like in some sense we're done. But I think the caveat is hiding in these lower order terms. So the result I showed had both in the upper and lower bound, kind of what Chapa was asking about, these little O of log 2 terms. And so we must ask the question then, well, how large does T need to be such that like we can kind of ignore this little O of log T term? Like we can upper bound there and graph by twice this Graves and Lie constant. Turns out in general, the best known lower order terms scale as the size of the decision set, pi. And for cases such as like tabula RL, this will correspond to needing T to be doubly exponential in the size of the state space. So like this is extremely asymptotic. Like these lower order terms are absolutely massive, and this is like not at all practical. Like this regime is like not something you're ever gonna probably be doing. And so while in some sense it is true that Graves and Lie does quantify the instance-dependent scaling, it doesn't. It quantifies it in a very asymptotic way, and we don't really have a great understanding of sort of what the non-asymptotics are, what the right lower order terms are in some sense. So to kind of motivate this further, I want to think about an example that I think will make some of these points clear. So let's say we have some model class, some sort of structure banded, and the decision set for this model class is to have 2 components. So you have A arms, and these are just banded arms. So that sort of corresponds to this part here. We can just think about these arms as a normal bandit, reward is 0, 1, whatever. The second part, you have N arms, denoted by these pi i's, and these arms are informative arms. So every time you play one of these arms, you get 0 reward. So these are not optimal. However, one of the N arms, if you play it, will just tell you the identity of the optimal arm. So in particular, for this bandit, the optimal arm is arm 1, and the largest reward. If you play pi 2, it will tell you arm 1. So all you need to do to solve this problem is you play pi 2, it tells you the optimal arm, and you're good to go. However, every other of these arms just gives you sort of a null observation. And so we'll make a model class then to be sort of the set of all such instances, where it has all possible informative and optimal arms. So you can show then for, as I just said, like the optimal thing here is just to play pi 2. And you can show that if you do this, the Graves and Lie constant scales as like O of 1. And this is better than if you treated this as a bandit, you ignore the informative arms, your Graves and Lie constant would scale at least, or the complexity would scale at least with A. And so like you're going to be doing better by pulling the informative. That's the optimal strategy. The caveat here is that there are N informative arms. There are N arms here, and only one is truly informative. And so you don't know a priori which of these arms is the informative arm. And so while sort of the optimal thing to do is play that informative arm, you need to find it first. And on average, it's going to take on order N pulls to do that. And because you get 0 rewards for each of those, you're going to pick up order N regret. So really, like while the Graves and Lie, the leading order term sort of scaled as like O of 1, there should be some lower order term that scales as N. So in this example, basically, again, if we knew the Graves and Lie allocation, we could just play it. If somebody told us this is the identity of the informative arm, we could just play it and it would be good. We just shoot the instance optimal right. But we need to learn this optimal allocation. We need to sort of like learn what this informative arm is. And there's going to be some cost to learning this allocation. And this applies in this example I just showed you, but it also applies more broadly. That if you look at what's going on with this Graves and Lie thing, it's really quantifying sort of this oracle, right? But we don't know what the oracle allocation is. And if you look sort of at the analyses for existing algorithms, these lower order O of log key terms, in some sense, correspond to roughly like learning this allocation. Like they do some exploration to sort of figure out what the right poles are for the Graves and Lie allocation, and then they play the Graves and Lie allocation. And so these algorithms that scale, has complexity scaling with size of pi, do some very like uniform exploration where they pull every decision some constant number of times, and then they just use that to like play the learn the optimal allocation. And so I want to remark then that this cost of learning the allocation, which in this case scaled as n, is not captured by the Graves and Lie complexity, as we saw. It is also, though, not captured by any other measure of probable hardness we're aware of. So like it doesn't, if you look at the example I just showed you to compute, say, the DEC or the information ratio, their leader dimension, etc., these will all scale with like A. They won't scale with N. And so there's a sort of like notion of dimension here, which is very important to achieve an instance optimality, which is not captured by really anything that we know. Yeah, question.
Could you explain how you on the Graves Lie allocation? Because I assume it's just how we need to explore to identify optimal arms, but
so the Graves Lie, when I say Graves Lie allocation, what I mean is, okay, you have this optimization problem, and you're optimizing over this eta.
Yeah.
That sort of the optimal value of eta is what I'm referring to as the Graves Lie allocation. Basically, what this is saying is like, if you have this allocation and you were to play it, it will tell you what it will collect enough information that you can eliminate suboptimal decisions while minimizing regret. So maybe to make this concrete, for multi-arm bandits, what this would be is it's going to tell you to pull every arm roughly 1 over gap squared times. Because what this will do is if you pull an arm 1 over gap squared times, you will be able to eliminate this arm, and you'll sort of like, that's the minimal amount of times you need to pull it to eliminate it, so the minimal amount of regret.
okay, just on the slide where you said it's constant, where there's one arm which reveals, why is it not order? Should
Because, yeah, that's a very good question. So the point is that this is like an oracle quantity in some sense. Like this depends on M star. So in this particular instance, there's the informative arm. It will sort of be reflected when you plug in M star into this equation. It's sort of assuming you know which arm is informative.
right.
So yeah.
Then a consistent algorithm surely would be one, but like both at least every arm once. You know. So it's a consistent algorithm, but happens to know and stuff.
So the lower, so I guess you don't, it's not really, so like for instance, a consistent algorithm could be an algorithm that just treats this like a bandit.
Yeah.
Like that doesn't use the informative arms at all.
Sure.
Like it doesn't actually, you don't have to use the informative arms to get sublinear regression. You have to use the informative arms to sort of like figure out to do the optimal thing for Graves and Lie.
So this, okay, clearly, when you say there are these algorithms which achieve this, are these consistent algorithms?
Yes. So the algorithms that do achieve this are, oftentimes, not all cases, but oftentimes they're doing more naive things. Like they will pull every decision once, or more than once.
Okay, but you notice these algorithms don't have access to knowing which arms are special are.
No. They all have access to the model class.
Yet they scale with the GLC, which in a way has access.
Right. That's sort of the tricky part here, is that like the GLC sort of to solve, if you knew M star and M, you could solve this problem.
Yeah.
And you'll give you an allocation and you'd be good. The issue is like this depends on M star. So you need to learn enough about M star to sort of like solve this problem.
So it almost sounds like there are algorithms which in a problem which has this magical arm that tells you the optimal arm are able to do as well as if you had already known the optimal arm to begin with, which sounds.
So we're not, there's no like, we're not saying there exists algorithms that satisfy this. What we're saying is like this.
There exist algorithms which give.
But it's not, so asymptotically this is the case. So, okay, maybe the thing to clear it up is like, we don't need to learn the identity of this optimal arm with sort of, with a probability of 1 over t, say. You only need to learn it actually with probability of 1 over log t. And so you can actually push, this is getting a little bit technical, you can push the cost of learning that into this term.
So effectively, this bound is telling me that in the sense that this holds, there exist algorithms, but as well as knowing straight away what the optimal arm is up to.
Asymptotically, up to lower order term.
Okay, which I guess reveals how ridiculous this statement is.
Yes, in
Okay,
some
fine.
sense, yeah.
I just couldn't cut up this
Yeah.
statement.
Yeah.
Sorry, so in your special arm instance, why wouldn't it regret just the end, the normal arm? Why would it scale the plot?
That goes back to this question that was asked earlier of like, basically, as t goes off to infinity, we sort of need to continually verify. For a fixed t, we sort of need to verify that the optimal arm is optimal with probability 1 over t. And that will scale with sort of like log t then, you know. So you're going to pick up a log t because you sort of need to verify this holds as f rising goes to t. So if we sort of verified it held with constant probability, I guess one thing I kind of abstracted away from this example was like how we actually instantiate it. There's like some noise here. Like, so otherwise you get like infinite tail divergences and stuff like that. So
Okay, so if there's no noise, presumably the GLC should be.
if there's, yeah, so that's a good point. If there's no noise, then it is 0 because like you have this tail divergence term which goes to infinity. So there's a little bit of noise. Yeah. Does that answer the question?
Yeah.
Okay. Yeah. Okay, I'm gonna keep moving, I think, because we still have more to cover. Okay, so this is kind of the problem then, is that like we need to learn this allocation. There's a cost to learning it, and this cost is not sort of captured in any complexity measure we know. And so what we want to try to sort of understand then in this work is can we sort of quantify this cost of learning and show that it's necessary? Okay, so the answer, at least we think, is yes. And so we came up with this idea, or this term, which we call the allocation estimation coefficient, which really quantifies this cost of learning this optimal allocation. Okay, so I'm just going to walk through this very slowly. So what this coefficient says is you first fix the model m bar, which we just consider a reference model. Not super important at the moment. And we'll define the AC to be this sort of min-max problem. So first it's going to take this minimum over two distributions, lambda and omega. And we're going to interpret lambda to be sort of a normalized Graves line allocation. So this is sort of a guess. You can think of this as a guess at the solution of the allocation to the Graves and Lie problem for, say, instance m bar. So that's one of the allocations. The other allocation is omega, and we think of this as an exploration allocation, which I'll sort of describe what that means in a second. So it's minimizing over these allocations, and then it's maximizing over instances in my model class that don't have lambda as a Graves and Lie allocation. Okay, so just to describe this more detail, what this is saying is that it's souping over models in m/mgl lambda. MGL of lambda is a set of instances such that lambda is a solution to the Graves and Lie problem. So what the soup is then over, it's over instances m, which do not have lambda as a solution to the Graves Lie problem. And I'll make this more concrete in a second too. So if you're not following here, we'll make it more concrete. The last term then corresponds to essentially the cost of distinguishing m bar from m under this exploration allocation omega. So again, if you have some instances m bar and m, and you're sort of drawing pi, your decision from omega, the KL divergence is sort of the statistical distance between them. And so this inverse of the statistical difference is sort of like saying how many samples we need to collect to just statistically distinguish. And I'll also define sort of this AEC of m without a reference model m bar, just a soup over model. Okay, so to make this a little bit even more concrete, let's just think about the case where m bar is equal to m star. Now in this case, lambda will be a solution to the Graves and Lie problem for m star. The reason this is the case is that if it's not, now this m bar becomes m star. So if m star is in this soup, then this is infinity, right? Because the KL divergence between m star and m star is 0. So we need to make sure that m star is not in this suprema. And the way to do that is we have to choose lambda, so it's a Graves and Lie allocation for m star. Okay, and so then if lambda is a Graves and Lie allocation for m star, what the supremum is over all instances m that have different Graves and Lie allocations from m star. And so what this really quantifies then in this case is the cost of distinguishing m star from instances with different solutions to the Graves and Lie problem. And we're taking this sort of infinitum then over omega, so it's saying for like sort of the best possible exploration distribution. And this is actually in some sense very analogous to the Graves and Lie constant itself, the grades and lie constant is sort of quantifying the cost of distinguishing M star from instances with different optimal decisions. This is quantifying the cost of distinguishing M star from instances with different optimal allocation. It's a very analogous thing. It's just like what we're distinguishing is a bit different. Okay, so let's think about this, how this works for this informative arm example I sort of described. So again, let's say we're in this case where the informative arm is arm 2. Now in this case, the grades and lie allocation, as I sort of described, would just put all the mass on arm 2. Okay, so in that case, when we think about this AAC, lambda will just put all the mass on arm 2, which implies that this set M\MGL lambda will be instances that have informative arm that is not 2, right? If an instance has informative arm 2, then lambda will be a grades and lie allocation for that. So this will simply correspond to all instances with different informative arm. So in this case, then the AEC quantifies the cost of distinguishing M bar from instances with different informative arms, which is precisely what we kind of like wanted to capture. This is really precisely quantifying the cost of like bringing this optimal, the informative arm. I also want to emphasize here that this isn't, you could have instances that have different optimal decisions. Like maybe the optimal arm is arm 3, but it has the same informative arm. The AEC won't distinguish between those arms because it doesn't care if it has a different optimal decision. It cares if it has a different optimal allocation. Okay, and so in this case then, we need to distinguish M bar from instances with different informative arms. The way we do this is basically we choose an allocation that sort of puts mass uniformly over the arms. And you can show that in this case, the AEC scales as like roughly at, yeah.
Why is lambda put everything on time 2 and nothing on?
Yeah, good question. Because like the thing is that
The allocation is like non-normal.
yeah, so so I'm kind of, there's a lot of like technical annoyances with like working with normalized versus unnormalized allocations, which I'm not going to talk about at all in this talk. So we're just thinking about distributions, like sort of think of this in mind. So what's going on here is that like this like when you actually like play an algorithm like this, what it will do is it'll say like allocate order log t samples to figure out what the optimal arm is, and then t minus log t samples will be played on the optimal arm. And so sort of the grades and lie allocation just corresponds to learning what the optimal arm is. But like when you actually like are playing, then the vast majority of the polls are just going to the optimal. Does that make sense? No, because lambda is really quantifying, is really saying how do you distinguish what the optimal arm is. It's not like, it's not trying to pull the optimal arm necessarily.
It's the solution to the GLC.
Yeah.
And also reasoning for taking
the reasoning is, I guess, like you could, I guess, write it down for a fixed lambda. Okay, I mean, the reasoning in some sense is that like this isn't sometimes like the best you could hope to do, right? Like you could sort of a best hope to have it for the minimum lambda. If you had it for a fixed lambda, it's always just going to be an upper bound of that. So we show that you can actually, as we'll see in like a few slides, you can get an upper bound that scales with the ADC that has this infinitum over lambda. So, I mean, it's the best you could hope for. And so if we can get it, then that would be sort of the best we might hope for, and we can get it. So
I'm expecting this to be in this case.
So the thing is that if you did the soup, it would be infinity, because then you could basically choose, like going back to sort of what I was saying here. If you had a soup over lambda here, you could choose lambda to not be a solution to the grades and lie problem for M star, in which case infinity. The soup would be like, yeah, huge. So you really want the inf for something like that. Okay, are people, does sort of this idea of the AEC make sense generally? Does any other questions? Okay, cool. So then the question is like, well, it kind of maybe it's intuitively reasonable. Is it actually like, does it work? Can we get something that scales with that? So it turns out the answer is yes. So there is this an algorithm we call a squared that for any instance M star has regret bounded as the grades and lie constant, so the correct leading order term, but then a lower order term that scales primarily with the AEC. And I'm finding various sort of other terms here having to do with say the minimum gap, the log covering number of my class, stuff like that. See the paper for sort of all the details on that. But the key point takeaway here is like, say in this example I just showed you, this informative example, you're going to get an N here. It's going to sort of precisely quantify the cost of like learning this informative arm. So like algorithmically, this actually does work. Like the AEC is really capturing something that we can implement. So yeah, basically this result implies that the AEC is sort of a sufficient measure of lower order complexity. And I want to emphasize again, this is like extremely general. Like we're making some assumptions on our model class. Again, see the paper for details on that. With regards to say like some, bounded log covering number, some smoothness or something, etc. But otherwise, like this just works. For you give me a model class, the algorithm will just work for this model class and get this return. I'll just mention as one last caveat, right? The results I'm going to present in the talk, I sort of take the minimum min gap in my model class. You can replace the min gap in this M star. You have to there's some caveats there, so I didn't put it in the talk to see the paper. The takeaway though from this is we can have there's an algorithm that has sort of regret that is instance optimal in the leading term, it's a straight line constant, and lower order term scaling as the AEC. So then the second question we want to ask is in some sense the AEC necessary? Again, intuitively we would think it is. You have to learn the optimal allocation to play it. So the answer to this is also yes. So I'm going to introduce this set, call it M opt of M bar. What M opt of M bar is the instances that sort of on the optimal decisions behave identically to M bar. So you can't distinguish instances in M opt of M bar from M bar by playing optimal decisions, but not super important for purposes of this talk. So we can show that unless log t is greater than the AEC for this M opt of M bar flow, so we're taking the supremum over M bar, no algorithm can simultaneously achieve the regret is bounded by twice the grades y constant, and that with constant probability, it's able to learn an approximately optimal allocation for the grades y problem. And so what this really says is that, at least in some sense, the AEC is a necessary measure of complexity. But in order to get regret, in order to have an algorithm that is grades y optimal, and that is playing an optimal allocation, or learns an optimal allocation, you have to pay the AEC. You have this burden that scales with the AEC. I'll also just remark, so again, the form in the AEC here is slightly different than what I put it in the upper bound. You can get a form that matches it exactly, but you have to replace the log t that is degrades the bound somewhat. So there's one sort of technical caveat I guess I will mention here. I'm going to have a lot of discussion on this in the paper. What this lower bound is saying is it's saying, how many samples do I need to collect to learn a solution of this with constant probability? Now, what I would really ideally like is sort of a lower bound and regret, or say a direct lower bound and regret. Turns out, for various technical reasons, this is pretty tricky to get. But if you're willing to make a slightly stronger assumption on your algorithm, for instance, that the second moment of the regret is bounded, you can basically get what I just said. Or rather than sort of having this constant probability thing, you can argue that if it's doing the grades y thing, it sort of has to pay this burden. And the intuition here is that any algorithm that hits grades y has to play the grades y allocation in expectation, but then getting something to constant probability from that in expectation turns out to be kind of tricky. So if you make some slightly stronger assumptions like bounded moments and whatnot, you can get it. Otherwise, it's not quite clear. But I think in the intuitive sense of what's going on here, this is really capturing what any intuitively correct algorithm would have to do. Any intuitively correct algorithm has to pay grades y allocation. And this lower bound says that to do that, you have to have an AEC burden. Okay, so let's just sort of think a little bit about comparing sort of upper and lower bounds here. So for our upper bound, we get that the upper bound, the regret is bounded by twice the grades y constant. We need that log t is greater than the AEC. If you look at the upper bound, once you have log t greater than this, you can just upper bound regret by twice grades y. And it turns out this is precisely actually the burden our lower bound gives. Our lower bound just says, you need to have log t greater than AEC. And so really, in some sense, these upper and lower bounds match quite closely. And I think, in some sense, really say that the right lower order term here is this AEC term, that it doesn't seem to in general be improvable. Yeah, so I think our results really show that this AEC captures a lower order term, I think takes some step at least towards there's like a complete characterization of what's going on with instance optimality. Okay. I'll just quickly go through a few corollaries and then explain at a very high level what the algorithm does. And I think I'm probably running out of time. Yeah. Questions?
What is this algorithm?
Yes. Next slide. Next slide. Let me just yeah. Good question. No, like you mean like sort of a, can you get like a minimax style graph with that? Yeah, our algorithm does not have like it does not also get square root t regret. It does not, and I think that's an interesting direction for future explorations. But just to give you some sense what this, so I sort of just argued the AEC is, it seems in some sense fundamental. So what does it scale like? I mean, the gist of this slide, I don't even need to maybe go through all these examples precisely, is at least for the standard classes of problems, say like multi-amp bandits, tabular RL, linear bandits, etc. You can sort of upper and lower bound the AEC by standard notions of dimension. Say in tabular RL, you can upper bound it by state, action, horizon, min, gap, stuff like that. You can also lower bound it by state, action, min, gap. Same thing with like linear bandits. And in general, like in all the classes we look at and have a lot of examples in the paper, this is true. So like bandits are bound at a looter dimension, you can upper bound the AEC by the looter dimension. Contextual bandits, you can upper bound it. Like it seems like it sort of just immediately gives you corollaries in all these cases. And really in all these cases, like our bounds either give you either improve on the state of the art. Like for tabular RL, we're the first to get sort of a lower order term that scales polynomially and problem parameters. Or it meets state of the art. So, you know, for linear bandits, for instance, we already actually have algorithms. Johannes has a really nice paper on this. On how do we get sort of polynomial lower order terms? So we can kind of match that dependence. And again, it's quite general. Like you give me a monoclass, we can calculate the AEC for it, and my algorithm immediately gives you that regret bound. Okay, so what is this algorithm? I just want to go through, I'll just go through it very quickly. So it's actually extremely simple. So for t equals 1 to t, we're going to proceed. Okay, it's going to first do something which is like sort of a test to see if it can explode. So it's going to look if there's some decision pi hat such that it can like guarantee pi hat is optimal with probability like 1 over t. If it does that, it can just plays pi hat. This is the exploitation phase. This is just saying, you know, yeah, I collected enough data that I can show my decision pi hat is optimal. I'm just going to play it. There's no reason not to play it in that case. Second phase is the exploration phase, and this is a more interesting phase. In the exploration phase, what it does is it plays some allocation. It chooses some decision pi hat to play, and it's drawn from some allocation, which is a mixture of two distributions, lambda s and omega s. And these lambda s and omega s is precisely you get it from just like solving the AEC. And so basically we maintain some estimate of a model, m hat, and we just solve the AEC for this m hat. We get two allocations out, and we just play a mixture of them. And then, you know, we collect some data we collect some observations from that. We update our estimate of the model, and we proceed. And for those of you familiar with someone like Dylan's work, as well as other people have been using this too, this is sort of just one of these online learning sort of estimation oracle type things. And this is the algorithm. Like this is all you do essentially. Like I'm hiding like a few very minor technical details here, but like this is really all you're doing. Like you're just solving the AEC problem. And again, this is like in some sense class agnostic. Like the structure of the class is encoded fully in the AEC problem. You give me a class, this algorithm can run on that. It can get this regret. And so I think one sort of nice observation from this then is that this complexity measure, this AEC, it immediately motivates an algorithm. Like it's not just some arbitrary complexity measure that quantifies something nice. Like it actually just tells you what to do. And again, I just want to emphasize that like it's quite simple, and indeed I'd say significantly simpler than like most works out there that get reasonable regret bounds. It's really just three components: this estimation oracle, this sort of explore, exploit test, and solving the AEC. Okay, do I have like 2 more minutes to like sort of maybe describe what's going on here, or should I wrap up? Okay. So I guess I'll just quickly explain on one slide kind of the intuition for this. So if lambda s, so there's two cases. So we're playing this allocation that's a mixture of lambda s and omega s. So first case one is lambda s is approximately greater than optimal for m star. So in this case, plain lambda s will just give us the instance optimal rate for m star. We're kind of like good to go. So this case is like not super interesting actually. The more interesting case is this lambda s is not greater than optimal for m star. So in this case, m star will be in this sort of set that we're suping over, m backslash m GL of lambda, which implies that omega s will actually distinguish m star from m hat of s. And you can sort of quantify how much information you're gaining from playing this omega in terms of the AUC. And then you can argue that if your estimation error is bounded, and it turns out it is in our case, it is bounded by a long number of exploration rounds, then you can only like have this case happen so many times. And the amount of times it happens scales with the AUC. We have some more detailed proof steps in the paper, but the basic idea here is that like, yeah, either you're playing grades in lie, or you're learning something about your model that will tell you what grades in lie is. And so you'll then play grades in lie eventually. And that's basically it. Yeah, so conclusion, yeah, the AAC plus grades in lie gives a fairly, I think, complete characterization of instance optimality. There's still, I think, a lot of open problems here. So I think one problem is, well, instance optimality and RL function approximation. So in principle, our results should extend, at least to model-based RL. We just worked it out for tabular. So I think there could be interesting things just like you're working out sort of our results for more general function approximation cases. I don't see any barriers to this. We just didn't do it. A question that was asked here: can we simultaneously achieve instance optimality and minimax optimality? Johannes has a nice algorithm that does this for linear bandits. Our algorithm does not. Not clear if it could. I think it could be interesting to look into. And then another question, is there pure exploration analog to the AUC? I think, so we considered regret. You could also look at sort of like best decision identification. I think it should extend, but we haven't worked that out, and I think it could be interesting to spend some time on that. So yeah, that was it. Thank you.
Questions?
Johannes?
Best understanding correctly that you're controlling the finite order term for the asymptotic allocation.
Sorry, say that again.
So you're controlling the finite times the lower order term for the asymptotic instance optimal.
Yeah.
Which is not necessarily the same as the finite time instance optimal. What would you agree there?
So I think the thing is that like, okay, so you can definitely get maybe different instance dependent bounds for sort of shorter time horizons. Like something that is not the Graves and Lie constant, right? Like say for instance, our goal is to identify an epsilon optimal action or an epsilon optimal policy. Like that's, the Graves and Lie doesn't like fully quantify this. So like there's definitely stuff going on there. We don't have a great understanding of this. Like I've done some work in like various RL settings trying to like come up with like reasonable measures. I think the tricky part is like you can't usually show lower bounds for these. So it's never quite clear like what is like tight. So you can get things that are reasonable, but like getting something that's tight is kind of tricky. So I think when you think about the Graves and Lie, it is a very like nice characterization. And so it is still, I mean, even our result you could say is somewhat asymptotic, and that like you have, it will, like, you need long t to be greater than the AUC for it to kick in. Like this could potentially be a pretty large burn still. So you might care about shorter time horizons. Yeah, I think there's interesting questions there that we don't know the answer to currently.
Something related to another layer of action. Take this action to find optimal in this layer.
Yeah. Yes, that's a good question. I think the AUC would really only capture the first level of that. Well, I guess it's not clear. Like I'd have to like think about this a little bit more. But I see what you're saying. It's sort of this, you put this like infinite regression, and it's not quite clear. I mean, I think the AAC might. I guess if you just go one level back, the AAC might capture that because then it could pull this omega distribution could just be the action that tells you sort of what the Graves and Lie. Okay, it could be the action that tells you what the informative action is. I think the omega. So in that case, it would probably work. I guess you could probably continue to regress that back, and it might just go all the way. Yeah. Honestly.
Anything on the ADC as tech EC for learning? Basically,
That's a good question.
we also see a bit better language also has a tech EC and also has is there like some connection?
Yeah, I think like at least in terms of how we prove the lower bound, it actually is very similar to the techniques that Dylan is using for these packed EC things in his other papers. So there's definitely connections there. I mean, it is in some sense a connection. It's just that like sort of the packed EC is really quantifying like the cost of learning the optimal decision. Ours is quantifying the cost of learning the optimal allocation. So so there is that connection in that like you're in both cases trying to quantify this complexity of learning something. It's just like what you're learning is different. Yeah.
Useless, but like intuitively, do you gain something by not caring about the suboptimal stuff? Just like creating the optimal thing.
Yeah, so I think like, I mean, so your goal if you're trying to get low regret, your goal is to play the optimal arm as much as possible and play the suboptimal arm as like little as possible. Right. So that's where I mean, that's why I guess the grades and Y constant is like not 0, because you do need to still like distinguish between the optimal decision and the suboptimal. And usually that means you have to play the suboptimal decision some number of times. The idea is like, can we just play these the like minimum amount of times possible? And that's kind of what grades and Y is.
Is the min-max programming the algorithm easy to solve?
No, I didn't mention this, but like it's not computationally efficient. That could be another open problem if this could actually be run. Yeah.
So at one point you mentioned that if you make a stronger assumption on the algorithm, that it has bounded moments, bounded second moment. Could you just expand on that again, like what that means and what is the result?
Yes. So what's going on there is this lower bound I showed you. The condition on it is basically like you need to pay the determinant to find an optimal Grayson Y allocation with constant probability. What you would like to say is that any algorithm that gets like low regret sort of finds an optimal Grayson Y allocation. So what you can say is that any algorithm that gets low regret, in expectation will be playing an allocation that are Grayson Y optimal. But you can't actually get it. We couldn't actually get a lower bound from just that statement. We needed something slightly stronger. If you go up to constant probability, you can get that. You can go through the lower bound. The trick is, so the thing though is that any reasonable algorithm and any sort of algorithm we actually know about would actually basically like satisfy this like constant probability in some sense. And so what we end up sort of arguing with this like second moment thing is that if you have an algorithm that has like the second moment of the regret is bounded nicely, then you can go from this like sort of expectation thing to a constant probability. You can argue that it is learning in a greater than Y optimal allocation with constant probability, and then the lower bound immediately applies.
And the second moment of the regret considered as a random variable, like assuming the
Yes.
so the algorithm is concentrating its
Right. So the idea is that like you can't have with constant probability that the algorithm gets regret as ordered T, or something like that.
Right.
Yeah.
So the issue of getting these max bounds.
I mean, so the issue is that like when you're exploring, so there's like sort of the two phases to the algorithm. You can show that when you're exploiting, you get almost 0 regret, or very small. The thing is, when you're exploiting, like other than saying that regret is like bounded by this Grayson Y constant, like you can't really say that much about it. Like the thing is, you would need to argue somehow that like you're playing the optimal action in this phase, like all but square root T of the time, and like it's not clear how to do this. Like it seems like you would have to do something like on top of playing this. Like you'd have to sort of like mix these allocations then with like playing the optimal decision, or you guess at the optimal decision like most of the time. And then it's not clear how the rates would extend in that case.
So in that case, for the pure exploration in the system setting, there is a check and stop algorithm. And it also has this parameter T's which is similar to the criteria that characterize the properties of the instance by using the pair algorithm.
Yeah.
So I wonder whether it is a generalization or
So the Grayson Y constant generalizes to pure exploration. Like maybe that's what you're getting at. Like you can definitely write down these upper and lower bounds for pure exploration in a fixed confidence setting. I guess The thing that maybe would be interesting then is that there is still this cost of learning and allocation. That's all algorithms seem to pay. So maybe you could extend the AEC to settings like this, where like sort of you have to then learn what the optimal allocation is for the sort of pure exploration groups. Okay, I think I'm probably way over time, so I should probably wrap up and let other people talk. But maybe if people have more questions, they can find me afterwards.